Hello. Today we will discuss problems from US Physics Olympiad year 2008 quarterfinals. For 60 minutes they'll get 4 problems. Problem number 1. A charged particle with a charge small q and mass m is given an initial kinetic energy k0 at the middle of a uniformly charged spherical region of total charge big Q and radius big R. Small q and big Q have opposite signs. The spherically charged region is not free to move. Throughout this problem, consider electrostatic forces only. Question A. Find the value of K0 such that the particle will just reach the boundary of the spherically charged region. So it means that our particle moving from the center to the border by straight line. So first of all we have to count what is electric field inside of this sphere, which is due to symmetry radial and going from the center. Let's take a small sphere, radius a small r. Inside of this small sphere we have a charge which could be counted using this equation. If we have total charge is big Q and this charge spread uniformly, the total charge inside smaller sphere will be proportional to cube of small radius. Second thing, due to symmetry we can tell that electric field from small sphere behave like electric field from point charge, and electric field created by outside sphere is 0 due to Gauss law. So it means that electric field equal this expression. We see that electric field is proportional to distance from the center. Now let's count what is potential difference between center and the border. For that we need to do integral using this formula. If we put our expression for electric field, we will get this expression, and finally we have this result. So total potential difference equal big Q over 8 pi epsilon 0 R. And now to count what is total energy needs to be total kinetic energy needs to get to this particle. We multiply this potential difference by charge of this particle. So this is the result for question A. Next point, question B. How much time does it take for the particle to reach the boundary of the region if it starts with the kinetic energy K0 found in part A? Let's check our answer for electric field in the first question. We can write immediately equation for motion for this particle. That's this one. A equal negative QE, and that's equal negative Q small q big Q over 4 pi epsilon 0 big R cube multiplied by R. Or if we rewrite it in regular form for motion, we have this expression. We see that we get just a regular equation for oscillation, for harmonic oscillation, because On the left part we have a second derivative from displacement, which is acceleration, and on the right side we have force proportional to this displacement. It means that we have a solution for angular frequency for this motion. We have omega square equal exactly this part of equation. And now to find what is total time to travel from the center to the border, we can first count what is period for this oscillation. That's this one, 2 pi over omega. And because in our case one period equal 4 times motion from center to border and back, like this, this and this, so we just need to divide this period by 4. So that will be our answer for part B. Problem number 2. A uniform pool ball of radius r and mass m begins at rest on a pool table. The ball is given a horizontal impulse j of a fixed magnitude at distance beta r above its center, where -1 less or equal to beta less or equal to 1. The coefficient of kinetic friction between the ball and the pool table is mu. You may assume the ball and the table are perfectly rigid. Ignore effects due to deformation. The moment of inertia about the center of mass of a solid sphere of mass m and the radius r is I0 equal 2 over 5 mr square. In such a problem, solution. In such problem, better to figure what axis of rotation we can choose. Usually we are choosing axis around which we have minimum possible torques. That will be any axis which is perpendicular to vector of j and which is stay in the plane of table. For such axis, let's see, we have all forces which are acting on this ball are force of friction, which are applying in the plane of table. Also we have normal force, and we have a gravity force, which are compensating each other. In any moment, angular momentum of this ball after this kick will be conserved. Let's count initial position. When we hit this ball with impulse j, we can count what is angular momentum for this ball around any axis which belong to this table and perpendicular to this j. That will be j multiplied by r and multiplied by 1 plus beta. That's a distance from this point of j. So that's the formula. After that, this kick, we have ball which is moving and rotating, and we have not connected yet velocity and angular velocity. But later, when ball is stopped to sliding, it has instantaneous rotation around axis of rotation, and we can write this equation: L equal I omega, where I is moment of inertia of this ball around axis of rotation, and the omega is final angular velocity. Due to parallel axis theorem, we can count what is moment of inertia. This is the formula. Moment of inertia equal to moment of inertia around center of mass plus mr square, where r is distance from axis of rotation to center of our ball. That will be 2 over 5 mr square plus mr square, which is 7 over 5 mr square. And now we can equalize our results, and we have this equation where omega now equal v over r, because there are no sliding. And finally we got the answer, v equal 5 over 7 multiplied by 1 plus beta multiplied by j over m. So that's the final velocity. Question B. For what value of beta does the ball immediately begin to roll without slipping, regardless of the value of mu? Now let's count what is initial velocity and what is initial angular velocity. To count what is initial velocity, we just write equation mv0 equal j. This is how we count what is the impulse for this ball. From other hand, we have after this impulse we have rotation around center of mass, and we can write this expression. I0 omega 0 equal j multiplied by distance from this axis of rotation, which is beta r. And now we can count what is v0 and what is omega 0. So for body not to slide, we have, and now we can put omega here and find what is beta. Finally, we can find that beta equal 2 over 5. Problem number 3. A block of mass m slides on a circular track of radius r, whose wall and floor both have coefficient of kinetic friction μ with the block. The size of the block is small compared to the radius of the track. The floor lies in a horizontal plane and the wall is vertical. The block is in constant contact with both the wall and the floor. The block has initial velocity v0. First question. Let the block have kinetic energy E after traveling through an angle theta. Derive an expression for dE over d theta in terms of g, r, mu, m, and E. So first of all, we can write expressions for force of friction, because only this force is responsible for change of kinetic energy. For the flow, we can call it Fx, and this is the expression for force of friction Fx. For the wall, we have force which is equal coefficient of friction multiplied by normal force, and normal force is responsible for centripetal acceleration. So we can write this expression. But we know that kinetic energy equal mv square over 2. So it means that we can rewrite our normal force. So we can rewrite our normal force in form of. So after that we can write expression for a change of kinetic energy. The change of kinetic energy equal work done by force of friction. So that's Fx plus Fy multiplied by delta L, where delta L is a path for a small period of time. And delta L equal radius multiplied by delta theta, where theta is angle. So finally we have this expression. Delta E equal negative mu multiplied by FGR plus 2E and everything multiplied by delta theta. And the answer for question A will look like this. Question B. Suppose the block circles the track exactly once before coming to halt. Determine V0 in terms of G, R and mu. Now we can split variables for the previous answer. We have this expression, and we can do integral for both parts. Left part will be from E to 0, and right part will be from 0 to 2 pi. This is our calculations. So left part looks like this, and integral for this function, that's just a logarithm, and when we put border meanings, finally we have this expression. After that we have expression like this. And now when we mention that energy equal mv square over 2, we can put this energy here and find that 1 plus v0 square over gr equal exponent from 4 mu pi. And finally our answer will be this one. V0 equal root from gr multiplied by exponent 4 mu pi minus 1. That's the answer for question B. Problem number 4. Two beads, each of mass small m, are free to slide on a rigid vertical hoop of mass big M. The beads are threaded on the hoop so that they cannot fall off of the hoop. They are released with negligible velocity at the top of the hoop and slide down to the bottom in opposite directions. The hoop remains vertical at all time. What is the maximum value of the ratio small m over big M such that the hoop always remains in contact with the ground? Neglect friction. Solution. So first we can count what is the acceleration of each bead for any position. Let's do this. Suppose that both beads now reach the angle theta on this picture. I show only one bead, but other is in the same position in opposite direction. Now we can count both accelerations, tangential and normal. tangential acceleration could be found from formula at equal negative g sine theta. And normal acceleration could be found from knowledge of velocity in this point. Velocity we can find from energy conservation. This is the equation. And now we can find what is v squared, this one. And we know that normal acceleration equal this expression. So in any point we can count what is tangential and normal acceleration. But we are interested in the total vertical acceleration in y direction. For that we have to find what is a projection of a tangential acceleration on axis y and projection of normal acceleration of axis y. So we need to multiply tangential by sine theta and multiply normal acceleration by cosine theta. And now we have to add them. So for this, after this operation, we can find that total ay equal this expression. Now let's see. Our bit moving vertically with this acceleration, but it creates by force of gravity and by a reaction from hoop. We can write this equation. So here we have may equal negative mg plus force from hoop, vertical force from hoop. So from here we can immediately find what is the vertical force from hoop. That will be this one. And now we can count what is maximum for this force. Maximum we can reach for angle with the cosine theta equal 1 over 3. So it means that force Fy equal negative 1/3 mg. If this force acting on a bead in negative direction, it means down. It means that this bead acting on a hoop with the same force. But because we have two beads, we acting on a hoop with the force 2/3 mg. It means that if we apply force greater than big mg, our hoop will jump. So solution will be when 2/3 mg less than big mg. And finally we have this relation. For this relation, small m over big M less than 3 over 2, this hoop will never jump. And there is other way to solve this problem. We don't need to split our acceleration by tangential and normal, because we already counted what is the velocity in any position. And we can just take a derivative from velocity and find what is acceleration in any position. So we already counted what is the velocity for an angle theta. This is the expression. And we can find what is the projection of this velocity on y direction. That will be this one. And it's negative because it's going down. Now let's take first derivative by time from this velocity. We have this expression. We can count this derivative. And we see that delta theta over delta t, that's omega. That's the angular velocity of this motion. and we know that angular velocity, that's just equal v over r, and we can use this formula for v and to substantiate it here. So finally we have acceleration equal this equation, and after simplification we can find that total acceleration will be like this. And if we check the acceleration in the first solution, that will be the same. So we have the same result.